All right, we're going to continue talking about effective values today. So at the end of our last class meeting, we developed the following relationships. The effective value of a periodic voltage waveform was given by the square root of 1 over the period of the waveform times the integral over 1 period of the waveform times the square of the waveform with respect to time. And we found that the effective value of a periodic current waveform was effectively the same thing. Then we worked an example in which we found the effective value of a series of rectangular pulses with a duty cycle X that was between 0% and 100%. Now we're going to find the effective value of a sinusoidal waveform. So once again, it doesn't matter whether or not it's a current or voltage. I'm just going to arbitrarily say that I have some current I of t of the form I am cosine omega t plus theta I amperes. Because we're squaring our signal, I'm going to go ahead and make you aware of a trig identity that I'm going to wind up using. Technically, I've already used it in this class before, and I used it numerous times in Circuits 1. And that trig identity is as follows. The cosine of some angle 1 times the cosine of some angle 2 is equal to 1/2 cosine angle 1 minus angle 2 plus 1/2 cosine of angle 1 plus angle 2. Since we're squaring this current waveform, angle 1 and angle 2 are literally the same thing. Okay. So another quick thing that we need to pay attention to is we're going to have to figure out what the period of our sinusoidal function is so that we can put that into the limits of our integration as well as multiply by 1 over the period, right? So let's say that we had a simple sinusoidal signal. So this is our current I of t. This is t. And we're dealing with a cosine function, so let's just pretend for now that our phase angle was 0 degrees. So that would look something like this, where this amount of time from one positive peak to the next positive peak is our period t. Do any of you guys remember how that period is related to either angular frequency or linear frequency? So our linear frequency f is just the reciprocal of our period, right? So frequency is effectively the number of cycles per second. Our period is the number of seconds in one cycle. Angular frequency is related to linear frequency by the relationship omega is equal to 2 pi f. So if we put those things together, we wind up finding that t is equal to 2 pi over omega, I believe. Sorry, I've got a headache and simple algebra is making my brain not want to work. Equals 2 pi over t. Yeah, 2 pi over omega. Okay. So taking all of that into account, our effective value for our current waveform would be the square root of 1 over 2 pi over omega. So that's going to look like omega over 2 pi times the integral from 0 to 2 pi over omega of our current waveform squared. So that's going to look like the magnitude of our current waveform, 1/2 times the magnitude of our current waveform squared plus 1/2 times the magnitude of our current waveform squared times cosine of twice omega t plus twice theta I. And all of this was integrated with respect to time. So what should the integral of this part I'm underlining in orange come out to be? So if I were to plot cosine squared, or cosine of twice omega t, on this same graph that I put cosine of omega t, it's going to look like effectively the same thing, except that it's going to go through its cycle twice as quickly. So it would look something like this, right? Well, I'm integrating over this duration t here. So I'm integrating over exactly 2 cycles of that double frequency waveform. So what's the integral of a sinusoidal function over any integer number of cycles? I disagree. 0, because exactly half of the time it's above the axis and exactly half of the time it's below the axis. So the integral of this entire term right here literally just looks like 0. Okay. So we're left with just this stuff over here. Okay. So we would have the square root of omega over 2 pi times the integral from 0 to 2 pi over omega of 1/2 the square of our current magnitude. And the square of our current magnitude is a constant that we can take outside of our integration, and the 1/2 is as well, right? So that's going to give us 1/2 Im squared times omega over 2 pi times the integral from 0 to 2 pi of dt. Sorry, 2 pi over omega dt. Well, the integral of dt from 0 to 2 pi over omega is literally just going to be 2 pi over omega. So this integral and this fraction right here wind up canceling each other out. And so what we see is that the effective value of our sinusoidal waveform is going to be the magnitude of our current divided by the square root of 2. The result here is independent of angular frequency omega and independent of phase angle. So it literally does not matter what our phase angle is or what our angular frequency is. The effective value of a cosine function is always just the magnitude divided by square root of 2. And what's really great about that is that here in the United States, we use 160 hertz as our linear frequency, or 120 pi radians per second as our angular frequency for all of our electrical systems. In Europe, it's 50 hertz or 100 pi radians per second. But if we're talking about effective values, it's the same regardless of where we're at, which means we can design anything for literally any country as long as we're using effective values. All right, so normally here, this is where I would go off and talk about complex power, but I'm not going to do that just yet because I kind of got a little bit out of sequence. I want to talk about instantaneous power in multi-frequency circuits first, and then we'll go into complex power. Okay. So let's say that I have a black box network. And it is sinusoidally excited. And we're able to measure the voltage drop across our network and the current flowing into our network as time domain functions, where, just for this example, I'm going to have my voltage have two frequency components and my current also have two frequency components. As you will very shortly see, the math is only going to get more ridiculous the more different frequency components we have. So two frequencies will be more than enough to illustrate how much of a pain in the ass this truly is. Okay. So let's say that we have a voltage Vm1 cosine omega 1t plus some phase angle theta V1 plus Vm2 cosine omega 2t plus some phase angle theta V2. And our current I of t can be expressed in a similar form. So Im1 cosine omega 1t plus theta I1 plus Im2 cosine omega 2t plus theta I2. The instantaneous power for our network is still going to be the product of our voltage waveform and our current waveform. And to make my life a little bit easier, I'm going to break things up. So I'm going to call this V1, this guy here, V2. This guy down here will be I1, and this guy down here will be I2. And so multiplying these together, we're going to wind up having V1 times I1 plus V1 times I2 plus V2 times I1 plus V2 times I2. And now I'm going to have to apply that trig identity I showed you guys a moment ago 4 different times. So when I multiply V1 and I1 together, I'm going to get 1/2 Vm1 Im1 cosine theta V1 minus theta I1 plus 1/2 Vm1 Im1 cosine twice omega 1 plus theta V1 plus theta I1, which is exactly the same thing that we got for the instantaneous power of a single frequency circuit. And now we get to the ridiculous bits. Okay. So to that, I am adding the following 6 terms in total. Okay. So now I'm going to multiply V1 times I2. So that's going to look like 1/2 Vm1 times Im2 cosine, and now I have to take the difference of these angles, right? So that's going to look like omega 1t plus theta V1 minus omega 2t plus theta I2, or omega 1 minus omega 2, all of that times time, plus theta V1 minus theta I2, plus 1/2 Vm1 Im2, and now I need to add those angles together. So cosine of omega 1 plus omega 2 t plus theta V1 1 plus theta I1. Now I'm going to multiply V2 times I1, and I'm going to get a similarly terrible looking thing. 1/2 VM2 IM2 cosine omega2 minus omega1 t plus theta V2 minus theta I1 plus 1/2, sorry, I put a W instead of a V, VM2 IM1 cosine omega1 plus omega2 t plus theta V2 plus theta I1. Hold on. Sorry, this theta I1 up here should have been a theta I2. Now I'm multiplying V2 times I2. Yes. VM2 times IM1. So let me fix, thank you for that. Yes. Yep. There we go. Okay. Now I'm multiplying V2 times I2. So V2 times I2 is going to look very similar to V1 times I1. So it'll be 1/2 VM2 IM2 cosine theta V2 minus theta I2, excuse me, plus 1/2 VM2 IM2 cosine twice omega2t plus theta V2 plus theta I2. All right, 8 terms. Now, let's look at some things here really quickly. This term right here that I've underlined in green, and this term right here that I've underlined in green, these are DC terms. So these guys effectively represent the average power in our multi-frequency circuit. Okay. Then we have this guy right here. So we have a term that's oscillating at a frequency of twice omega1. This term right here is oscillating at a frequency of twice omega2. This term and this term are oscillating at a frequency of omega1 plus omega2. And this term and this term are oscillating at a frequency of the difference between omega1 and omega2. And I can say that because I know that cosine of x and cosine of negative x are the same thing. So omega1 minus omega2 times t looks like omega2 minus omega1 times t. It's the same excitation frequency. So in a system containing only 2 frequencies, we wind up having power oscillating at 5 different frequencies, right? If I had done a 3 frequency system, we would have wound up with 9 because it winds up being 2n plus 1 frequencies in our system. So this is brutal to do. Okay, especially because the overwhelming majority of the time, we actually only really care about average power, right? That's why when we get into complex power and all that kind of stuff, we don't really think about the instantaneous power anymore. We just make sure everything is rated correctly. Okay? So this conundrum right here is actually one of the main reasons why effective values were developed. The math is tedious when we're at 1 frequency, but at multiple frequencies, it becomes terrifying to figure out what's going on. So let's figure out how to determine the effective value of a multi-frequency circuit, right? So realistically, I would wind up integrating this thing over the period of whatever our voltage waveform is, which is the same as the period of our current waveform is. Well, way up here, we effectively just found out that integrating integrating a sinusoidal function over an integer multiple of the periods goes away. And so what that's going to translate to is effectively all of our terms that are time varying, the integral of those over the period of our voltage or current waveform actually wind up going away as well. And so we only wind up having to care about our DC components. So in a system like this, I'm going to just call this Y effective. So it doesn't matter if it's a voltage or a current. Our effective value is going to be related to the effective values of just the individual frequency terms, right? So let's call this Y effective, comma, omega 1. And our second term would be Y effective at our angular frequency omega 2. And we could go on from there, right? So let's put a plus sign here. Y effective omega 3 all the way out to Y effective at omega sub n. Okay. What we're going to have to do to get the true effective value is we're going to wind up squaring each of these individual effective value terms and then taking the square root of the sum of those. So for example, if I had let's make our life easy here, a resistor as part of a larger circuit, and let's make this a 1 ohm resistor so things are just wildly easy. Okay. This is my voltage V of t across this resistor. And let's say that V of t is equal to 5 cosine 10t plus 20 cosine 5t volts. The effective value of our voltage drop across our resistor would simply be the square root of 5 divided by square root of 2 quantity squared plus 20 divided by square root of quantity, square root of 2 quantity squared. And that would give us a much easier path for calculating powers and all of that kind of stuff than using the time domain function by a large degree. All right. So to summarize this portion of today's lecture, solving for instantaneous power in a multi-frequency circuit is a nightmare. So average power can be done effectively using effective values, and that's what we're going to get into here. So this is going to start our talk on complex power. We're also going to talk about complex power in our next class meeting as well. So anything that I don't cover today, we'll just get to in our next class meeting. And realistically, I'd like to spend a little bit of time here answering any questions that you guys may have about what didn't make sense about this material when you saw it in Circuits 1. Because this is literally just straight review. So the only purpose of it is to clarify any questions that you may have had when you took it in Circuits 1. Okay. All right. So let's start by looking, let's call this complex power. So let's start by looking at our average power relationship in a sinusoidally excited circuit, right? Our average power we found earlier was 1/2 times the magnitude of the voltage times the magnitude of the current times the cosine of theta V minus theta I. That is the DC part of the instantaneous power that we learned about in Wednesday's class meeting, okay? All I'm going to do here is I'm going to split that 1/2 up into 1 divided by the square root of 2 multiplied by 1 divided by the square root of 2. So that effectively I have Vm divided by the square root of 2 times Im divided by the square root of 2 times the cosine of theta V minus theta I. And recognizing that in a sinusoidal steady state system, Vm over the square root of 2 is nothing more than the effective voltage. I'm left with V effective times I effective times the cosine of theta V minus theta I. Okay. So our average power here has been expressed in terms of our effective values. And really, all that did was get rid of that pesky 1/2 sign out front that was preventing us from just using our DC relationships. Now we've still got that cosine theta V minus theta I thing out there. So in order to sort that part out, we are going to introduce another domain to analyze circuits in, okay? So a time domain voltage is a signal of the form Vm cosine omega t plus theta V, right? That's what we've been using for our time domain representation. And we know that we can convert any time domain signal into a phasor or frequency domain signal by effectively just keeping the magnitude of the cosine representation of that signal, keeping the phase angle of the cosine representation of that signal, and then throwing everything else away, right? So our phasor representation of this voltage would be V is equal to Vm with an angle of theta V. Well, we know that the magnitude of our voltage is related to our effective values. So we're now going to introduce a new domain, and I'm going to call this the RMS frequency domain. And I'm going to designate an RMS phasor by putting a tilde over it, as opposed to the bar that I've been putting for general complex numbers. Okay. And so this is literally just taking my phasor voltage and dividing it by the square root of 2. Because we know that the effective value of a sinusoidal signal is just square root of 2 times smaller than its magnitude, we can get a new phasor that is an RMS quantity by dividing our phasor by the square root of 2. So this is simply Vm over the square root of 2 with an angle of theta V, or V effective with an angle of theta V. So it carries the exact same information as our phasor voltage does. It just uses the effective value instead of the magnitude of the sinusoidal signal. Okay.
Had to convert it back over the time.
Correct. Absolutely correct. All right. So looking at this representation of our voltage signal and understanding that there would be a effectively identical representation for a RMS phasor current, right? That would just be Im over the square root of 2 with an angle of theta I, or I effective. Somebody much smarter than me noticed that the average power is simply the real part of the following mathematical operation. The RMS phasor voltage times the complex conjugate of the RMS phasor current. Right? So let's expand on this a little bit, okay? So if I have an RMS phasor voltage, whatever it happens to be, and I multiply that by the conjugate of the RMS phasor current as a polar form complex number, this is going to look like the magnitude of my RMS phasor voltage times the magnitude of my RMS phasor current, and it will have an angle of theta V minus theta I. And so this effectively looks like V effective, I effective with an angle of theta V minus theta I. And then the real part of that so I'm just putting this caret here to tell you I'm putting all of this crap inside of those braces. Comes out to be V effective, I effective, cosine of theta V minus theta I. The imaginary part would be the same thing, except it would be replaced with a sine function. Right? So electrical engineers have decided to call the product of our RMS phasor voltage and the conjugate of our RMS phasor current a complex power. Okay, so complex power S, by definition, is simply an RMS phasor voltage times the complex conjugate of an RMS phasor current. Now let's talk about units of complex power real quickly, okay? So we're multiplying a voltage times a current. So the units seem like they should be watts, right? Because voltage times current, or volts times amps, is a watt. And that's not wrong, but it's not right either. So electrical engineers have made up their own unit to deal with complex power because they want to be able to see when you're dealing with complex power versus when you're dealing with average power at a glance. So we have decided upon the unit of a volt ampere, VA, as the unit for complex power. Dimensionally, it is identical to a watt, but we don't call it a watt because watt is power. It also has an imaginary component, okay? All right, so since our complex power is a complex number, we can split it up into a rectangular form complex number or a polar form complex number. So that's literally what I'm going to do right here, okay? So in rectangular form, well, we already know what the real part is. So we have V effective times I effective times the cosine of theta V minus theta I. And we call this average power, which is exactly what it was before. No change has been made whatsoever. And as we all know, the units of average power is the watt. We're also going to have some imaginary part. And the imaginary part of our complex power is going to be V effective, I effective, sine theta V minus theta I. And everything there without the J is what is commonly referred to as the reactive power. And once again, we make up a unit so that we can distinguish this from average power and complex power. And so the units of reactive power are the volt amperes reactive. In a shorthand notation, we typically refer to the average power as capital P, and we may or may not choose to include the subscript average or AVG. And then our reactive power is typically given the symbol Q. So in rectangular form, our complex power is simply P plus JQ, where P is this relationship and Q is this relationship. And realistically, they're not that difficult to learn, memorize, etc., but you actually don't ever really need to use them because the calculators that we use can break complex numbers up into real and imaginary parts. So as long as we remember that the real part of our calculation is the average power, and the average part of our the imaginary part of our calculation is the reactive power, as long as we can multiply V times I conjugate, we never have to remember any of these other formulas. Okay. So let's talk about what average power represents and what reactive power represents. Okay. Average power is the power that is consumed by a load and is able to be converted into heat. So we call that the energy that's capable of performing work, and it's literally just an energy transformation, right? We're transforming electrical energy into heat energy. We're saying that's what our average power represents. Our reactive power is what's going on with the inductive and capacitive parts of our associated loads. So we were talking, I think just Wednesday, about how the average power absorbed by an inductor or the average power absorbed by a capacitor is zero, because exactly half of the time the element is absorbing power and exactly half of the time the element is sending that power back to the source. The reactive power is what takes care of that action, okay? So it's simply temporary energy storage in our system, okay? Even though it's imaginary, which is a whole nother bag of cats, all that really means is that it's 90 degrees out of phase with the real stuff. It plays an integral role in our utility grid. Without having forms of reactive power in the forms of capacitor banks and things like that in our utility grid, it could not instantaneously adapt to the changing loads that it faces when, say, everyone gets home at 5 o'clock and starts cooking dinner at the same time, right? Everybody turning on their oven, their air conditioning unit, and all that kind of jazz at the same time literally can cause a blackout in the power grid if there isn't enough reactive power available to help ride that out. In fact, that happened in Great Britain during the World Cup. Everybody went to make a cup of tea at the same damn time and literally caused a blackout in London. I believe so, yeah. Something similar happened down in New Orleans during Beyonce's halftime show at the Super Bowl. It literally caused a citywide blackout because so many people went and got up to do things at the same time that consumed electricity, and the utility company wasn't prepared. There wasn't enough VARs in the system to handle it, and there was a blackout. So while it's imaginary, it is literally critical to the healthy operation of our utility grid. For those of you that go do internships and all of that kind of stuff for electric utilities, you'll learn all about interesting things like static VAR compensators and all of that stuff, which are really just really honking big capacitors that they switch into the system when they know we are going to need a boost of energy to ride an event out. And that's largely what goes on with power factor correction and all that kind of stuff, which we're going to see in a little bit. Okay, so average power is effectively the portion of complex power that's associated with resistors, and it's all about converting electrical energy into heat and mechanical work. Average power is what's associated with capacitors and inductors, and it's all about having some form of energy storage for when stuff goes awry. All right. In polar form, we have V effective times I effective times the angle theta V minus theta I. Let me put brackets around that. And this quantity, V effective times I effective, also has a special name. So we call this the apparent power. And because apparent power is nothing more than the magnitude of our complex power, it is also measured in volt amperes. This angle, theta V minus theta I, is what's known as the power factor angle. Because it's an angle, its units are probably in degrees, but it could be radians. It really doesn't matter because we know how to switch back and forth between those very easily, right? So in polar form, this is typically written as the magnitude of S, our complex power, with an angle of theta S, where theta S represents our power factor angle. So before we go into the long spiel about what power factor means, let's talk a little bit about what apparent power means, okay? I feel like most, if not all of you guys are too young to own your own home and have had to go shopping for a generator or something like that. But maybe some of you are big enough dorks like me to where you've had to shop for an uninterruptible power supply for your computer, or in my case, a CPAP because I'm an old man. When you go shopping for generators, UPSs, and things like that, typically it gives you two different ratings. One rating is measured in watts, and the other rating is measured in volt amperes. That volt ampere rating is the apparent power that that device can handle. So apparent power is literally just the product of the RMS value of the voltage times the RMS value of the current. So it kind of represents almost a worst case condition because there are no phase angles taken into account that could possibly cause the value to be a little smaller, right? So if the voltage and the current were perfectly in phase, the apparent power is how much power am I going to have? In a real system, they're never exactly in phase because there's real parts of the load and reactive parts of the load. But so the apparent power is, like I said, a worst case scenario. And so that's what we typically use as a design criteria for a system. So when you're sizing, like when you're trying to decide what size of wires or conductors to install in a system or something like that, you really look at the apparent power draw to tell you what your expected current should be. Because you know that that's the worst case scenario of what your current could ever be in that system. So if you were trying to, let's say that you had something that was rated for 240, 2400 volt amperes, right? So a 2400 VA rating would mean here in the US that you're probably dealing with a 120 volt RMS voltage, which means you could at most handle 20 amps RMS of current, which means you need to make sure that whatever conductors you're installing in this system are capable of withstanding 20 amps of RMS current without melting the insulation, which would cause shorts and potentially burn the system down. That's what volt amperes are used for. If the voltage is a fixed value, like it is here in the United States for any receptacle, where it's going to be either 120 volts for a standard household receptacle, 240 volts for a receptacle that's used for like your oven, your dryer, and things like that, you can easily figure out what currents you can handle just by looking at the apparent power rating of your load and then say, this is what wire I need for this thing. Really, you have to add in a 25% safety factor according to the NEC code and all of that kind of good stuff, but that's a problem for another day. Okay. So apparent power is just used for designing a system effectively. All right, and so now let's open up the can of worms that is the power factor. So power factor is in some ways a measure of the electrical efficiency of a system. So mathematically, it is given by the ratio of the average power to the apparent power. If we scroll up here just a touch, we can see that our average power is V effective, I effective times cosine of theta V minus theta I. And our apparent power is just V effective times I effective. So this ratio literally just comes out to be the cosine of our power factor angle, theta S. Okay. So let's talk about why the power factor is measured this way. And it all has to do with the electric utilities. Okay. So average power is what we as consumers pay for. That's what our energy bill is comprised of. How much average power we consumed over the duration of a month, because power times time is energy, right? So our energy bill is nothing more than the total amount of average power we consumed multiplied by all of the time in a month. Well, the electric utility had to design for the worst case scenario, right? Which means they have to put in infrastructure to potentially be able to carry more current than anybody would actually need to draw at any given time or something like that, right? So average power is what we as consumers pay for, and apparent power is effectively what the electric utility pays to generate. So from their business perspective, they want the average power to be as close to the apparent power as possible so that all of the energy they're generating is getting paid for by a consumer. Okay? In some instances, like most homes, that will be the case. Okay? But for some, say, large-scale manufacturing places, it will not be the case because they have large loads like induction motors and things like that that are going to have a lot of reactive power associated with those loads. And so at an installation where they have a large amount of reactive power draw, like a manufacturing plant, there are usually restrictions on how low your power factor is allowed to go before they fine you. And correcting that is all of what power factor correction or power factor compensation, that's literally all it is figuring out what can I put in my system to avoid paying a fine to the electric utility. We'll talk about that in detail on Monday. Okay. Now let's talk about power factor, or at least the power factor angle is kind of a more abstract concept because it can tell us a whole lot about our system, okay? So if we look at the power factor as simply a mathematical relationship, it is the cosine of some angle. That means that there are strict limits on what value the power factor can have, right? It can only range from +1 to -1. And so that's why we tend to view it as a measure of efficiency, because it can mean we're either 100% efficient in consuming power on one side of the spectrum and 100% efficient in supplying power on the other side of the spectrum. And there in the middle, when our power factor is 0, means we're doing a garbage job of supplying or absorbing the power in our system. So typically speaking, or not typically speaking, always speaking. So when zero degrees is less than theta s is less than, I'm hesitating here because I'm unsure of whether or not I'm about to say 90 degrees or 180 degrees. And so let me explain what I mean by that, right? So if I were to restrict this to be 90 degrees, effectively all I'm saying is I'm looking at absorbed power. If I go over the 90 to 180 degree mark, that's effectively making my resistance quantity a negative quantity, which means that power is actually being supplied, right? So realistically, anytime our angle is positive, I'll just call it 180 degrees. And this will take into account both absorbing and supplying. So whenever our power factor angle is between 0 degrees and 180 degrees, we say that our power factor is a lagging quantity. Okay. All that means is that our current is lagging our voltage in our system. Okay. So what types of systems have current lagging the voltage? An inductive load, absolutely, but not a purely inductive load, okay? So this means effectively that whatever our load is, has a resistance quantity that is non-zero and a reactance quantity that is greater than 0. Let me draw that R a little bit better. And again, resistance effectively looking less than 0 means that we are just supplying energy to our system. When 0 degrees is greater than, our power factor angle is greater than negative 180 degrees, we call this a leading power factor, which means our current leads our voltage in our system. And this means that we have a capacitive load. So our load has a resistance value that is not equal to 0, and it has a negative reactance. when theta S is equal to plus or minus, nope, not going to do that. 0 degrees or 180 degrees. Our power factor is unity. So at 0 degrees, the cosine of 0 is positive 1. And that means that we are absorbing power at 100% efficiency. When we're at 180 degrees, we have the cosine of 180 degrees, which is negative 1, which means we're supplying power at 100% efficiency. Okay. And so that's why that power factor is called unity. Unity is just a fancy word for 1. Okay. When our power factor is at unity, our system is neither leading nor lagging. The only way that this can happen is if the voltage drop, our current and voltage are either perfectly in phase or perfectly 180 degrees out of phase, right? So that means there can't be any inductance or capacitance in our system whatsoever. So we could say from here that our load has R is not equal to 0, and our reactance is exactly equal to 0. And then lastly, when theta S is exactly equal to plus or minus 90 degrees, our power factor is 0. The repercussions of this are that our load has no resistance and is purely reactive. Right. So this should cover literally the entire spectrum of any power factor angle that we could ever see, because it's all of the angles from positive 180 to negative 180 degrees. Telling us whether or not our power factor is going to be a leading quantity, a lagging quantity, whether it's unity, whether it's nothing, all of that. And also from what those angles are, we can infer what type of load is connected to our source. Okay. So I feel like this is a pretty appropriate background on power factor. And then when we talk about power factor correction in our next class meeting, we'll have a good idea of what's going on. Do you guys remember anything about power triangles? A little bit? Okay, I'll go through it really, really quickly because I've already done 90% of the legwork there. Okay. So a power triangle is nothing more than just a visual aid to remember how everything is related. Okay. So for an inductive load, where for this case specifically, we're going to say R is greater than 0 and X is greater than 0. Our complex power plotted out would look something like this. So this is my real axis. This is my imaginary axis. And for an inductive load, my complex power will be something like this. So this is the complex power absorbed by my load. The projection of this complex power onto the real axis is my average power. The projection of the complex power onto my imaginary axis is my reactive power. the length of my complex power vector is my apparent power, and the angle formed between my complex power and the real axis is my power factor angle. So all a power triangle does is just reinforce the relationship that the real part of complex power is average power. The imaginary part of complex power is reactive power. The magnitude of the complex power is the apparent power. The angle of the complex power is the power factor angle. It's literally the same material we covered a while ago, except it's represented in a graphical form. Okay? So effectively, S is equal to V times I conjugate, which can be expressed as P plus JQ, or the magnitude of S angle things. That's power triangle. All right, we've got 10 minutes left of class. I don't think that's quite enough time for me to go through my alternative relationships for complex power that are really just shortcuts by exploiting how complex numbers work. So we can knock those out at the beginning of our class meeting on Monday. Before we knock off for today, does anybody have any questions about any of the stuff that we've covered that you would like clarified? Toby, how may I help you?
Average power is the same thing as real power.
Yes, absolutely. Yes, sir. Rectangular, exponential, and polar. That being said, me personally, 99% of the time, it's going to be in polar form. The other 1% is split between rectangular and exponential. I effectively never represent a RMS phasor voltage or a phasor voltage as a rectangular form complex number, like practically never. Yes, sir.
Can you scroll back up to that long ass equation we did that had like 8 different parts where you underlined everything?
Sure.
Can you explain what each color means?
Sure. Okay, absolutely. So the ones that I've underlined in green are DC. Okay, because VM1, IM1, theta V1, and theta I1, those are all constants. So the ones that I have underlined in green are literally just DC terms. Okay. The one that I underlined in orange is oscillating at a frequency of twice omega 1. The one that I underlined in blue is oscillating at a frequency of twice omega 2. Okay. The ones that I underlined in pink are oscillating at a frequency of omega 1 plus omega 2. And the ones that I underlined in lavender are oscillating at a frequency of the difference between omega 1 and omega 2. So I just underlined them in different colors so that we could see how many different frequencies shake out of that terrifying relationship. So 2 frequencies go in, 5 frequencies come out. Gross, 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 gross.
So for a question on using instantaneous power, what would that, if you were going to ask a question about it, would we write all that out?
Yeah, if I were going to ask you a question, at most it would have exactly 2 frequencies because that is all I could ever want to make you suffer through. So it would literally just be if you were able to find. So if you watch the video on analysis of multi-frequency circuits, you would know that you have to use superposition to analyze a multi-frequency circuit because the impedance can't have 2 different values at the same time, right? So each frequency, every circuit component will have its own associated impedance. So this equation right here, as big and ugly and terrifying as it is, would actually allow you to just use the results of that analysis and plug phasor relationships directly in to calculate the power without having to do any work on your own. So VM1 would be the magnitude of phasor voltage at omega 1. VM2 would be the magnitude of the phasor voltage at omega 2, and so on and so forth. Yes, sir.
Add
Correct.
So that's what that is, right?
Yeah. Yep, that's exactly right.
And there's no collapsing to be done through identity.
So there is some collapsing that can be done. And so what I mean by that specifically, the term in green, this is a DC term, and this is a DC term, so they can be added together. That's just going to be a number plus a number. This term in lavender is at omega 2 minus omega 1, because cosine of omega 1 minus omega 2 is the same thing as cosine of omega 1 minus omega, effectively cosine of x and cosine of negative x are the same thing. So realistically, these two terms in lavender could also be lumped together because they're at the same frequency. The two terms in pink could be lumped together because they're at the same frequency. So you could condense this down from 8 terms to 5, but 5 as small as you can make it.
So with this frequency, you have, or at least you have.
No, you will have 5 terms. Well, let me rephrase that. Assuming that omega 1 and omega 2, neither of them are 0, you will get 5 terms. If one of them is 0, you will get 3 terms. Yeah. If one of them is 0, you'll have a DC term, omega 1, and twice omega 1. Yeah. But if omega 1 and omega 2 both are not equal to 0 and are not equal to each other, you're getting 5 terms.
How does the circuit have?
So the short answer is, what if I connected 2 different analog wave function generators in series and set them at 2 different frequencies? That would be one way to do it. It's a dumb way to do it, but that could be something, right? So where you see circuits that operate at multiple frequencies most often in real life are radios and things like that, where there's usually going to be some DC stuff. Then there's going to be your frequency that your message signal is, and then the frequency that your carrier signal is. So think about human hearing. What is the frequency range over which a human is capable of hearing a sound? Anybody know what that is? Exactly right, 20 hertz to 20 kilohertz, okay? So that is what sound is traditionally broadcast at. It's usually actually a little bit more narrow range than that, which is why recorded sound sounds different than live sound. So when you're hearing something off your radio, it's an electrical signal that's somewhere in between 20 hertz and 20 kilohertz. Radio frequencies, or excuse me, radio stations broadcast. So if it's an AM station, which I'm sure none of you guys listen to because you don't listen to talk radio and bullshit like that, that's at usually like 1500 kilohertz and stuff like that. So I think it's like 900 kilohertz up to around 2000 kilohertz or so. For FM radio, I think it's 86 megahertz to 106 megahertz or something like that, ballpark that. And then for satellite radio communication, it's usually in the gigahertz range, right? Well, we can't hear at the gigahertz range or the kilohertz or thousands of kilohertz range or the megahertz range. So we have a carrier signal that our message signal is superimposed on top of. So somewhere in that communication system, there are DC signals and low frequency AC signals and very high frequency AC signals all at the same time. And in some parts of those systems, those signals interact with each other. Yeah. So anyway. Another example that I like to give is to talk about the country of Japan. So Japan was occupied by the United States and Europe after World War II. And so effectively there's a river that separates the large part of the main island, and the US occupied one side of that river and Europe occupied the other side of that river. And when they helped to rebuild after we dropped the nuclear weapons on them, Everything that the US built was designed to operate at 60 hertz, and everything that the Europeans built was designed for a frequency of 50 hertz. And so across that river, there have to be frequency conversion stations that convert 50 hertz to 60 hertz or 60 hertz to 50 hertz so that their country has a single utility grid. Everything in that country has to be designed to work at both frequencies because it's the same outlet wherever you are in the country, but the frequency of your power isn't the same. They also use 100 volts instead of 120, although Europe uses 230. So yeah. Anyway, I honestly don't know.
Oh, then it's actually be like their base system, but since Europe uses, where did they get 230 from?
I also don't know. So Europe is interesting. So the 230 that's used in Europe is pretty darn similar to the 240 that's used here in the States, right? So the electricity, unless you live in a large apartment complex, the electricity that goes to your home is actually 240 volts. We use what's called a split phase system. So it's a center tap transformer. We'll talk a little bit about this when we get into power and all that kind of jazz. But effectively that 240 volts from one hot wire to the next hot wire is split by a neutral wire in the middle so that you can get 120 or effectively negative 120. So our smaller appliances are designed to work on 120, and usually the polarity does not matter at all. And then our larger appliances, like our dryers, ovens, and things like that, HVAC systems, usually use the full 240 volts that's supplied to our house. Well, in Europe, everything just gets the 230 volts. They don't have a split phase system like we do. So one of the advantages of a split phase system is that if we were to accidentally stick a knife or a fork into our outlets, we will get shocked less than we would if we did the exact same thing in Europe because the magnitude of the voltages is always going to be smaller. So in the US, it is arguably a little bit safer because we use 120 for practically everything as opposed to 230 for literally everything. Yeah, so anyway, that's just a rant about things.
Now, what if an outlet was running at 55 volts?
What?
55 volts.
What is going at 55?
Okay, so what if like what if your outlet's set like 55 volts?
If your outlet is reading 55 volts, you need to hire an electrician very, very quickly.
Because I watched a video like a few weeks ago. This guy went to India for vacation. He brought all his like his probes and everything. He stayed in this nasty hotel and he decided to stick in an outlet read 55 volts.
That seems incredibly low. I don't know what voltages are commonly used in Asia, but that seems really, really low. And potentially, well, I was going to say potentially dangerous. So you guys haven't learned about transformers yet, but effectively power in has to equal power out. So if you're operating at a low voltage, that typically means you're also operating at a high current. Or if you're operating at a high voltage, you're operating at a low current. So here in the US, you have a slightly smaller risk of electrical shock, but the current's higher, so that might be the thing that kills you. Whereas in Europe, the voltage is higher, but the current's a little lower, so it's a questionable degree of safety either way. But anyway.
So that's
Huh?
So what voltage or current?
So realistically, I think it's as little as 10 milliamps of current passes through your heart, you're dead. Luckily for us, the resistance of the human body is very large usually. So it takes a considerable amount of current to actually look like 10 milliamps across your